Okay, so let's get through this final lemma that's hopefully kind of dispels all the mystery of what this x prime chain represents or what it is, and um, or maybe instead it confuses you even more, and either thing is okay. So let's see how we do. So to pick up from where we left off, we have these two chains, x and x prime. X prime sort of popped up kind of all of a sudden. As soon as we had x prime. That was lemma 1. And both, right, the transitions, are the ones that we know, right, pxy and p prime xy, right, those were the one-step transition probabilities for them respectively. And then lemma 2 said, well, look, now both of them share the same stationary distribution pi. They said, okay, great. And then now lemma 3 is hopefully going to tell us something, a bit more meaningful. So first what we're going to do is suppose both chains start according to their stationary distribution. So we've seen this before, right? We showed, for example, that when a Markov chain starts in its stationary distribution, it stays in its stationary distribution, right? And starting in its stationary distribution just means, for the chain x, it just means that the probability that x naught, right, meaning x0, x at time 0 is equal to x with probability pi x, right? And the same true for x prime, right? The probability that x prime naught is equal to x, that probability is pi x, right? And so, if you were to sort of simulate this on a computer, you would sample a random state from the distribution pi, right? Just like you can sample random numbers from a normal distribution, you would sample a random number from pi, and you say, okay, now I have this state. Let me give it to x and tell it, run from that, right? Starts at that state, right, x, and then it's going to evolve according to its transition probabilities, which are the pxy's. And then you do the same thing for x prime. You sample a random state from the distribution pi. You say, okay, x prime, you start on that state, and then you kind of move according to your transition probabilities, right? Those are the p primes. So what happens? Here's the punchline. So for any sequence of states, and this is a path, right? This is, you can think of it as a path, right? It's a sequence of states, basically, which are describing a way in which either one of these chains, right? Both of them are, running on the state space S. So this is just saying, here's a proposal for where you could go, right? Moving one step at a time, right? So you could start at state little xk, move to state little xk plus 1, and end up all the way at state little xl. And here L is just, positive integer greater than k, which is also a non-negative integer. So then, not surprisingly, the k and the l, they represent kind of times. And so, if you look at this left-hand side, right, we're going to have essentially two probabilities that are equal to each other. But let's go one at a time. Let's look at the left one. So the left one concerns the chain x, and it's essentially talking about a trip that x took from, it started at time k. At time k, it was in state little xk. And then the dot 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 means that, the next one that I kind of glossed over there is xk plus 1 is equal to little xk plus 1, and so on, all the way up to the final kind of endpoint of the trip. This is the final time when the trip ended, and here xl is in state little xl. So the left-hand side is easy, right? It's just basically saying, here's the event. The event is a trip that a Markov chain x took, starting at time k, ending up at time l, and it went through this path. This one should be a little bit more confusing, but let's kind of dig into it slowly. So first of all, this is concerning the chain x prime, right, not x. And you'll notice that the sequence of states is exactly the same. So the first one I wrote here is xk. The next one, in this dot 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 would be xk plus 1, then all the way up to little xk xl, right? So the sequence, right, the path is exactly the same, but what you'll notice is that time here is written in reverse. So at the end of the trip, x prime was in xk. But for x, that was true at the beginning of the trip. Whereas at the beginning of the trip, x prime was in xl, which is where x was at the end of the trip, right? And so this may throw you a little bit for a loop, right? You kind of don't know what to make of this. First of all, I mean, I'll give you an example that hopefully should explain this a little bit about what this means. But one thing to kind of notice is that the way you write this sequence, it doesn't matter what order you put here, right? This is just the probability of event A and event, or like event, say A1 and event A2 and event A3 all the way up to, you know, the final event, right? And so when you have a probability of an and of a bunch of events, it doesn't matter what order you put them in. So you could just flip this around, right, and write it from, you know, right to left, right? So you would start writing this one first and then move backwards and writing this one last, right? And that would basically say, well, here, look, x prime, now you can think of it as moving forward in time, starting at xk and ending up at time L. But then you'll notice that the actual states that it went through would be written backwards, right? So if you wrote that trend, you know, this sequence forward in time, not backwards in time like I did, you would then just have to reverse the states themselves, going from xl all the way up to time xk. So here's an example you could think of to maybe give you a little bit more intuition if it's missing right now. So the idea is that if you kind of, you know, you have these two chains and they're, you know, running wild on their state space S, and you take, you know, two video cameras, right, and you record each of them. You have kind of video camera 1 and you point that one at the chain X and it's following X, and then you have some other camera, the second camera 2, which you're gonna point at the chain X prime, and it's gonna record or make videos of that chain, right? And so you kind of record all these videos and then you kind of bring them home and you open up your laptop, you put all these videos in and you start looking at them. And so the idea is that this event here, right, can be viewed as you just, you know, putting in the video of the chain X, right, and you're just playing it from, you know, the beginning all the way to the end. This one is interpreted differently. Here you take the video from the camera that was recording X prime and you put it to the back of the tape, right, or the video, right, you put it all the way to the end of the video and then you play the video backwards. And when you do that, the two chains look indistinguishable in the sense of probabilities, of course, right? So basically all the videos that you took, if you played all the videos of X going forward and you took the videos for X prime and you played them backwards, the two videos would be completely identical. You would not be able to tell which one was X and which one was X prime. And for this specific reason, X prime constructed in the way that we did, right, with these transition probabilities, is called the time reverse chain for X, right? So it's not doing the same thing it's not doing the same exact thing as what X is doing, but it's doing everything backwards, right? Or rather, when you play the movie for X prime backwards, it looks exactly like X, but not forward, just backwards, right? So hopefully that gives you a little bit of intuition for the name time reverse chain, and also where kind of all this comes from, right? And it's a neat way that it all fits together. So, you know, I'll kind of try to, in the summary for the lecture, try to kind of one more time summarize all these results. But for now, let's try to go through the proof, right, which is a little bit more tedious than the ones that we've seen for lemmas 1 and 2. Right, so what do we do, right? We usually, you know, pick one side and we want to get to the other, and here I kind of arbitrarily, I'm going to try to read from left to right. So I'm going to start on this one and I'm going to hope to end on here, right? And honestly, it shouldn't make a difference because both sides have kind of the same structure, so, you know, intuitively the steps should really not matter that much, right? The sides look almost identical, just in terms of a different chain. So I'm going to start on the left side, that's what I have here, and then I'm going to make this equality. So how do I get this step? So in this step, I took this joint event probability and I conditioned on this path, which is basically the entire path without the very last step, right? So you see how this path ends on xl minus 1. So I conditioned, right? From here, I used conditioning to condition on this event, right? And then I picked up, obviously, a conditional probability, right? This is the, in fact, there's another step hiding here, right? In this, right, this one-step transition probability in kind of an intermediate step was actually the probability that xl is equal to little xl, right? So just this ending part, conditioned on this sequence right here, x little xk all the way up to little xl minus 1, right? That's what this was. But then by the Markov property, you say, well, you know, the whole path is irrelevant. It's just the most recent state that matters. And so you get, you know, the transition from xl minus 1 to xl. And this makes, you know, a lot of sense, right? It's sort of, this is the probability of the whole path, which should be the same as the probability of the partial path, times one more probability to get from, you know, the previous step to the final one, the one that we want, xl, right? The one that was ending right there. So it's a pretty useful exercise to fill in the blanks here. Hopefully you see it, or if not, maybe write it up on paper quickly. If you keep applying this over and over, if you want, you can, you know, if you want kind of full rigor, you can try to use induction here, but you know, or you can just keep applying the same exact thing that we just did to this joint probability. You'll very quickly end up at, you know, what's left, right? If I keep cutting this down one at a time, you know, boom, boom, all the way, I'll just end up, eventually I'll end up with only one thing left, which is this, which is what I have here, right? This is xk is equal to little xk. And what was left, well, it's the product of all my one-step transition probabilities, going from m equals k up to l minus 1, right? So I have pxk to xk plus 1, then xk plus 1 to xk plus 2, all the way up to, why is it l minus 1? Well, it's got to be because the final transition had to be between xl minus 1 up to xl, right? That was the final ending state. So hopefully this part is clear, and this one right here should follow directly by, right, what we had in a lecture where we proved that a chain that starts in stationary distribution is always, you know, always remains in its stationary distribution. And that's exactly what the next line says, right? It's taking this probability, using the fact that x started in pi, and therefore it stayed in pi, and so at any time thereafter, and in this case time k, it had to be, right, in that stationary distribution as well. And so, you know, from that line to here, or in that step, I just replaced the probability that xk is equal to little xk by pi xk. Right, and the other part, right, the product of one-step transitions, right, that stayed the same. Next step is easy. Also, all I did was plug in the definition for pi, or not the definition for pi, but solving, definition for the transition probability p, right? All I did was solve for p in terms of the p prime. Why am I doing this? Well, you know, I have to get to this side, and this side clearly concerns the chain x prime. So I have to somehow pick up the one-step transitions for that chain, which are right here, and that's what got me here, right? So I picked up a whole mess of other things, unfortunately, right? Hopefully this all goes away, but I was after getting here, right? All right, that was the intuition, right? I had to start here, and then I don't really know what to do, but, you know, I always have my one-step transition probability, so I tried to get to those, and then I had this relationship right there, which is what was applied here to get me these p primes, and then hopefully the rest of this mess will just go away and make our lives easier. And in fact it does, right? That's what happened right here. So how did this happen? Well, if you look at this product here, this ratio, right, these terms kind of cancel each other out one after another. So for example, the very first one here is m equals k, in the denominator is pi xk, and that cancels this guy right here. The top one, pi of xk plus 1, is going to cancel the one in the next product, which is going to be in the denominator, right? So as this product gets incremented, right, this same pi of this state here is going to appear in the denominator and it's going to cancel it. So if you go through, hopefully you can convince yourself that this is correct, right? That all these denominators, numerators are going to cancel each other, but there would be a leftover. And the leftover here is pi xl. Why pi xl? Well, it's the one when you unroll this product, the very last term didn't have a cancellation buddy, right, so to speak, right? There was no next one, and so the pi xl had to stay, right? So unfortunately we had this one, or maybe fortunately, let's see. This one got left over, and the one-step transitions, those, you know, clearly they had to stay, right? I couldn't do anything with them, nor do I want to. So the next step is, I mean, at this point you kind of see what's happening, right? We're just kind of trying to reverse engineer backwards, right? We're kind of trying to read backwards, but now we have x prime on our hands, right? Because we want to get to here. So, you know, hopefully you see how this comes about, right? This comes about because x prime started in its stationary distribution pi, and therefore it stayed there, and that's why I can replace pi xl by, oops, looks like I missed an L here. Right, so let's see, I need an L here. Oh no, that's not the one that I want. So I can put any time index here, right? So hopefully that's agreed upon, right? It's up to me to pick one, but you know, I can be clever or stupid here, right? But you know, clearly this is the point that I'm trying to get at, right? So not this one, sorry, I'm trying to get at this one. So if I'm playing it smart, I'm going to put a k there, but I could really put any number there, right? This is the, you know, once a chain starts in its stationary distribution, it stays there, and therefore any time can go into this subscript here, and that would make the sequence of steps true. But you know, the only way I get this right is if I put a k here. I don't know why I missed that. If I put a k here, then you know I have some hope, because that's what I'm trying to recreate, right? So there's a lot of ways to kind of, a lot of dumb moves, but that one hopefully it's going to turn out to be a smart move. And again, this all stays the same as it was. Let's see, is it, no, I did one more thing in that step just to hurry it up. So hopefully you see that this product is the exact same one as this one. All I've done is flip the order in which the index is going, right? And you know, it doesn't matter how I, right? There's another way to say this, is that the product is commutative, right? You know, if I take 3 times 5 is the same as 5 times 3, that's all I'm doing here, right? I just wrote the product in a different order, right? It doesn't matter how I multiply these numbers. And then the rest, right, is kind of hopefully smooth sailing, right? This part right here should remind you of right here, right, going from there to here, and that's what I've done, right? So we can try to think about how it's happening. First of all, you'll notice that these one-step transition probabilities, they don't tell you anything about what time the chain is doing this, right? It's saying that the chain is moving from xm plus 1 to xm, but it's not saying at what time, and you get to pick. Why is that? Because the chain is time homogeneous, right? So it doesn't matter what time it was. You know that the one-step transition probability applies at any time, because the Markov chain is time homogeneous. So so basically all it comes down to is picking the right sequence of times. And you know, here I've started at the very last state, so xl to xl minus 1, right? So here's my xl, and I've chosen, right, I've chosen that to happen at time k. Didn't have to, right? Could have started at anyone, but I'm trying to prove this statement, so I chose time k here, right? And the next one is obviously x prime k plus 1 is xl minus 1, and then all the way up to, I didn't fill everything in, right, to this, all the way up to time l minus 1, at which point the chain is in state k minus 1, right? That's the very last, well, the very last product of the sum is actually this guy right here, So this here is really written to be symmetric with this, and kind of maybe on your own you can walk and see why that's true, right? All I've done was sort of unwind it backwards just for a different chain, and writing, picking the, listing the states. Here I listed them backwards in order to put time going forward, just as we did it here, right? So that was kind of the setup. The reason for flipping the sum around is that so I could apply the exact same reasoning used to obtain this equality here. And so from here is the same thing as going from there to there, right? It's just conditioning on the path, right? And the conditioning is conditioning on this whole sequence here. And so this goes away and just becomes whatever was there, which is x prime L is equal to little xl, right? So this is, I'm being a bit quick. Hopefully you are following, or try to really write this down and convince yourself that all the steps are legitimate. And then the final kind of, to kind of seal the deal here, right? All you have to recognize again is that it doesn't matter how I list this, right? A joint probability of events, right? You can list it in any which way you like. And so this is actually the same exact thing as that, right? Just listed backwards. Instead of writing it as time moving forwards and the path going backwards, I wrote it, you can write it as time moving right backwards with the path kind of moving forward. And so, can kind of consider this lemma proved, and let's see kind of in the next clip what the big picture is again.